Okay, hi there. I'm Stephen T. Lauade, and today I'm going to talk about RAND, the CRT function, and what has happened to it in C++11. Answer: nothing. It's not even deprecated, which is kind of sad. But there is at least replacement functionality in C++11 that you should totally be using. So RAND considered harmful. Let me show you some code. Okay, so here's a little program I wrote. It's C++, even though it doesn't really look like C++. What's wrong with this? But wait, you might be saying, hey, I bet you everything's wrong. Haha, problem solved. Answer: no, there are many redeeming qualities that this code has. For example, it includes all the headers that it needs. All the headers that it's including are actually needed. They're sorted in sorted order. The braces are delicious. I mean, if you don't like these braces, you are wrong. I'm just saying. And non-trivially, %d, that is the correct format specifier for int. You might be saying printf kind of an abomination, but if you're going to use it, at least get the types right and actually that expression there that's int. So that's cool. And I omitted the return 0 and argc argv. I see examples coming all the time with that stuff. Like, it's unnecessary, omit it. Okay, so that's what's right with the code. So that's everything. Isn't it awesome? Well, no. This code is terrible. It's awful. So take a look at it for a bit, like 10 seconds, and try to imagine how many things are wrong with this code. Can you enumerate them all? I've got a lot of white space on the slide. It's all going to be filled with orange boxes in like a second. Okay, so what's wrong with this code? Well, problem number 1, null. I was just hammering on how this is an abomination on a couple days ago. So never use null, always use null putter. But what are we giving it to? Oh wait, this is the CRT function time. This updates once every second. Yeah, it says implementation defined in the CRT. Everybody uses a tick count of a second. So that means if you write this program and you run it, it'll totally compile. And you run it quickly, like twice in a single second, it outputs the same output. That's kind of crummy. Or maybe you've got a bunch of clients that are all running the same program. If they start it on the same tick of the clock, they're going to get the same output. Ew. But wait, what are we giving time null to? We're giving it to SRAND. Well, let's compile at warning level 4, whatever your favorite warning level is. And if your compiler is nice, it'll complain, oh wait, time is returning a 64-bit time t, unless you're using a horrible option, but it's 64-bit by default. And SRAND takes unsigned int. Possible loss of data, you're truncating. That's an annoying warning. And hey, unsigned int, that's 32-bit. That means that SRAND takes a 32-bit seed even if you want to give it more entropy. This is bad, especially if you've got multiple clients, you're running multiple simulations, and you would like more than 32 bits of entropy. So that's terrible. Okay, so that's like everything that's wrong with that line. I tried really hard to think. I couldn't see anything else wrong with that line. That semicolon is kind of innocent, so I left it black. Okay, but wait, there's another line. Okay, so this RAND call. RAND has an awful range. The standard guarantees that there's a range of at least 32K, but not necessarily anymore. And in some implementations, like VC, it actually is 0 to 32K. That's like really, really tiny. If you want, 64K, sorry, that's not enough. Okay, but what else is terrible about RAND? You go look up in Wikipedia. RAND is typically implemented with what's called a linear congruential generator. This is like a multiply and a shift, and then you're done, and like a mask. These are really low-quality random numbers. If you use them to generate like 3D points, they like line up in hyperplanes. Wikipedia has like a cool little diagram that's awful, like really poor statistical properties. And also, it has a really short period. You run RAND for long enough, and it'll start repeating the sequence of numbers. So that's like super crummy. But wait, I'm not done. I want numbers here in the range 0 to 99 inclusive, so I'm saying a mod. This is actually really awful, because even assuming that RAND returns perfectly uniform numbers, which is probably a bad assumption, this introduces bias. You get a non-uniform distribution. So there's two separate parts here. Don't use RAND, and don't say mod whatever. And I see people doing this all the time. Like Hello World example, somebody's writing their first game engine. They need some random numbers. They say mod n. Don't do that. OK, so what's wrong with mod n? Here I've got source and dest. I just want to give them nice names. Let's just assume that RAND is returning perfectly uniform results, which it doesn't. And then we say mod 100 to get 0 to 99. This introduces non-uniformity. Does everybody see why? This is actually pretty simple. So the reason why is imagine all the possible inputs. The range 0 to 99 inclusive maps to 0 to 99. Awesome. And then if you go up to 100, that gets moduloed back down to 0, and that's cool. But wait, what about the end of the range? You get to the end of the range, and 32K 700, Well, we end up at 32,767, and then we stop. So that means actually the numbers 0 through 67 inclusive are more likely to be generated because there's one more range of inputs that can generate it. This is awful, not just because those things are more probable, but because you have actually wrecked the average. This slightly decreases the average because the lower numbers are more likely than the higher numbers. Now, yeah, it's only like one part in 327, 328, but that's awful. Like, why introduce bias? And in some contexts, this could actually be a really big deal. So this is really modulo's fault. This happens whenever your input range is not cleanly divisible by the size of your output range. We could put any generator in there, not just RAND, and modulo would still be wrong. So that's bad. So now some people, actually, if you've got your computers open, you can say, you can Google Stack Overflow scale RAND. I actually checked Bing. It returns the right result, which is cool. And there's a Stack Overflow thing that says, how do I scale the output of RAND? Terrible advice. So this is actually taken from Stack Overflow, tiny adjustment because they wanted 0 through 100 inclusive, and my example uses 0 through 100 exclusive, but it's the exact same code. So they say, okay, I'm going to multiply it by 1.0 and get some doubles in there. Then I'm going to divide it by RANDmax, which is a constant. In this case, it's 32K on VC. And then I'm going to multiply it by the number that I want. So basically, get a double, scale it down, scale it up, and we're done, right? No, this is hilariously non-uniform. Like Stack Overflow permits like editing. I don't know how this has survived on the site because it's terrible. Whoever suggested it, why is this hilariously non-uniform? Again, think about the inputs, or just run it. The problem is that there's only one output of RAND that can produce the maximum number. If you look at what this expression does, here I've grayed out all the things that are common. The highest value that RAND can output, which is RANDmax, multiplied by 1.0, divided by itself, times 99 gives you 99. Anything less, even 32,766, when you treat it as a double and then divide by the max input, you get like 98.99 something something. Then you truncate and you get 98. So that means that your output, which really should be 0 through 99 inclusive, generates 99 with extremely low but non-zero probability. That's like hilariously non-uniform. Do not do this. So some people get clever. They're like, oh, you've got some off by 1 error, so I'm gonna fix it a little. I'm going to fix it for you. So this is double treachery. That's what I say. There's no long double treachery joke. I just want to let you know that I thought of it and I restrained myself. Okay, now if you take source and multiply by 1.0 and then divide by the maximum plus 1 and then multiply by the exclusive part that you don't want, this is what I call subtly non-uniform. So it resolves the problem of it being very difficult to generate 99. And if you just took a quick glance, it would look like, hey, it's uniform, floating points, totally smooth, right? Wrong. This is awful. And you know what? It's awful for the exact same reason that modulo 100 is awful, because some outputs are less likely. If you run this, and you can actually get perfect results. You don't need to do statistical tests or anything. Just pass in all the numbers from 0 to 32,767 inclusive. Some outputs will be generated 327 times. Others will be generated 328 times. And I actually have a list here of the ones that are less likely to be output. They're not all multiples of 3. It sort of shifts a little. But like 3, 6, and 9 are less likely than 0, 1, and 2, and so forth. This is bad. Now, admittedly, it's not as bad as modulo because it doesn't completely wreck the average. At least the ones here that are less likely are spread throughout the range. But it's still non-uniform, even assuming perfect uniformity of the input. Why is this? It's the pigeonhole principle. If you have 32,767 pigeons, in addition to a mess, that means that you cannot put them in 100 pigeonholes without having more pigeons in some pigeonholes than others. Nothing can do this if you're not willing to throw away data or ask for more data. So floating point will not fix your problems. Okay, so maybe you're saying, okay, yeah, that's caused by RAND's tiny range. If I had a bigger range, I wouldn't care about that so much. This is still bad. Even if your input range is 0 to the 2 to the 32 exclusive or 2 to the 64, you're still introducing that non-uniformity model, trying to get to 0, 100. It's reduced because your input has so many bits, but it's still not eliminated. And I don't know about you, but when I write code, I like it to be absolutely correct, not just good enough. Also, and this occurs especially for library implementers, what if somebody is asking you for more bits? So what I refer to this as, what if IEEE runs out of bits. The problem is, imagine you want something like scale down a 2 to the 64 input to something like 10 to the 18th. That's like, I don't even want to say what power that is. I'm going to say like quadrillion. It's going to be wrong. But that's like 2 to the 59.8. So that we can actually shrink it down, and that's like 2 to the 4 smaller. So we definitely have enough input there. You would expect that to not be too bad. But the problem is double, if you go look at Wikipedia, only has 53 bits of significant precision. That means that just encoding it in a double is going to lose information. Really poor statistical properties. So like I say, say you have a problem, you decide to use floating point. Now you have 2.00001 problems. Don't mess with floating point, at least not here. I treat it with respect and fear. Okay, so yesterday I was talking to actually a professional developer, and they were saying, I've heard about this random header that was voted into C++11 from TR1. I'm sort of scared because it's got so much stuff, and it does have a lot of stuff. It's got engines and engine adapters and type defs, and then this other thing called random device, and I don't know which one to use. Well, the answer is a lot of that stuff exists for like scientific programmers who actually need to like replicate some scientific paper that used a Knuth-B generator, but the vast majority of even very advanced programmers don't need any of this stuff. So what I'm going to say is you can just ignore all of the engines and engine adapters in C++11 except for 3 of them. 3 are cool. Those are random device, MT19937, and _64. That stands for Mersenne Twister, and the reason why you have to use those type defs is because they're just type defs for the Mersenne Twister engine, but with very, very special constants that were specified by a big, famous paper. You really can't use the engine with any other constants. Don't even try. Always go through the type defs. And random also has a bunch of things called distributions. It has this really cool model. The other confusing thing about random is it's got all this stuff, and it's not immediately clear how to put it together, but it is really elegantly designed. I love this header. The idea is it separates the notion of an engine, which is just some opaque black box that spits out random bits that are very high quality, and then a distribution which shapes those random bits into some integer or floating output according to some distribution you want. You got your Poisson distribution, and your normal distribution, and some that I can't pronounce, things like that. And they're all good distributions. Like if you need, your Cauchy distribution, go for it. But the vast majority of the time, normal industry programmers are probably just going to want 2 things: uniform int distribution and uniform real distribution. So I'm going to focus on uniform int distribution because that's going to do the 0 to 99 that we wanted. But if you want the other distributions, they're totally there. Just don't use piecewise linear in VC because it's got a bug reported that we need to fix. Okay, so now let's transform that horrible example into a nicer example using C++11. Random, by the way, is in air quotes for simple reason because to reduce the complexity of the sample, I'm using a fixed seed. So here, 1729 is a deterministic 32-bit seed that I just chose at random. And so when I run this program, it'll output the same result from the Mersenne Twister engine. So MT is this engine object, and it's going to generate random numbers in the range 0 to 2 to the 32 exclusive. Technically, it's supposed to do like unsigned int, but I'm just going to say that it's 2 to the 32. Then it's going to be passed through this thing called a uniform int distribution. And you can control the type. So you can say, I want ints, or I want uint64ts, or whatever. It defaults to int, but I like to put the type there. Here I just want ints. And then note that when you pass the range to disk, you might be expecting inclusive exclusive because the STL loves that, and it is awesome for iterators. But for distributions, it uses double inclusive. Why is that? Well, imagine that you want, say you're working with unsigned int, and you want 0 to 2 to the 32. Now, that would be kind of silly given that your engine's already that, but maybe you're giving it unsigned short, or uint 16t, and you want 0 to 2 to the 16 minus 1. If we were working with inclusive exclusive ranges, how do you express a number that's bigger than your type? That's kind of bad. So that's why it says inclusive inclusive, so you can express every range even if it happens to involve the max number. And then to invoke this thing, we call dist, which is a function object, and we pass it the engine. And you can think of this as running the engine filtered or viewed through the distribution. So if we wanted an actual non-deterministic program, that's very simple. We can construct a random device, which is the other engine I mentioned that you can use, and invoke it once. And this creates a non-deterministic 32-bit seed that will be different every time you run the program. Now, this is 32-bit, and you might be thinking, oh, wait, he was just slamming, SRAM for having 32-bit seeds. The thing that I'm not showing here is that Mersenne Twister actually has a separate interface that allows you to fill its state, which is quite large, with more random bits if you need. Most of the time, it's okay to have a 32-bit seed, but if you need to put more entropy in your Mersenne Twister, you can totally do that. You just need like a seed sequence and you're done. I'm just not depicting it here for lack of time. So when should you choose this Mersenne Twister versus random device? So Mersenne Twister, if you go read on Wikipedia, which is where everybody learns everything now, it's said to be extremely fast. And I always knew it was fast, but then I actually tested it on my local dev box. It is blazingly fast. It was able to output random numbers at 500 megabytes a second. That is a ton of random information. Divided by my clock speed, or my clock speed divided by that, it's 6.5 cycles per byte. And we're not like, SIMD optimized. We haven't even looked at the perf too much. And it was able to generate numbers that fast. That's pretty awesome. That'll vary across implementations and hardware. But you should expect that Mersenne Twister is just psychotically fast. You should basically never be caring about its performance. It's also has very high quality. That means that the numbers that it produces are distributed very smoothly, and you cannot distinguish them from true randomness except using the most sensitive statistical tests. Like, get an army of PhDs, put them in a room for a year, and they can find maybe one test that'll distinguish it from truly random data. Also, the name MT19937 comes from a Mersenne prime that's used in its construction, and it's actually guaranteed to have a period of 2 to the 19937 minus 1. That means it's never going to repeat for the lifetime of the universe. You don't even need to worry about that. And it's also equidistributed in 623 dimensions, so you don't have that problem with the hyperplanes that Wikipedia shows you. It's seedable, which is cool, like I mentioned. That means that you can replicate a run. This is useful in, say, Monte Carlo simulations. It's useful in even games where you're like, okay, I'd like to reload this save file with the exact same seed so I can play this outcome multiple different ways. And it's also reproducible, which is a term that I'm using that's strictly stronger than seedable. It means that, say somebody publishes a paper that was using Mersenne Twister's output, if they then compile that source code on another platform, Mersenne Twister will output the same random numbers because it doesn't use just some algorithm that the implementers chose. It uses a standard mandated algorithm that must produce exact output. If you look at the standard, it says, we require that the 10,000th outputted value be blah, 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 which basically says you've got to use this algorithm. So you don't need to worry about it varying across implementations. Underscore 64 is the same. It uses a different algorithm that generates 64 bits at a time. You can use that one. It basically depends on the bitness of the architecture you're using. Now, random device is sort of the opposite. It is possibly slow. I timed it on my local machine using VC, and it output pure entropy at 1.93 megabytes per second. And that's actually pretty fast. You probably don't need more than 2 megs a second of pure entropy. But that's like over 1,000 cycles per byte. So you probably shouldn't be using that as your primary source of entropy. Now, it's strongly platform dependent. I looked on GCC's libstd C++ page, talked about new features, and they said that as of 4.8 on Ivy Bridge, they can use a cool hardware random number generator on the chip, and that spits out pure entropy at like 6 gigabits a second. That's pretty cool. I've put that on my to-do list. And I don't know what libc C++ does for Clang. I didn't check, but I thought about it. And also, random device has this cool quality that it is intended to be cryptographically secure. Now, you have to check your documentation to see if your implementers guarantee that. VC guarantees this. We call rand_s from the CRT. And what that means is that the output, I'll get to questions at the end, that the output cannot be distinguished from truly random data, and even given all of the output to date, an attacker looking at that and using an army of supercomputers cannot guess what the next number is going to be. Mersenne Twister, for all of its wonderful qualities, it is not cryptographically secure. If you see enough of a Mersenne Twister's output, you can deduce its internal state and figure out everything it's ever going to produce in the future. cryptographic security is harder to do. It's slower. So Mercian Twister does not attempt to achieve that, but Random Device can if the implementer so documents. But of course, that means that it's not seedable and it's not reproducible because it's generating a totally fresh random number every time. You really should check the documentation because the standard permits it to use a deterministic engine, although I would say that any standard implementer who does that on a machine that's capable of generating pure entropy is a bad implementer and should feel bad. Okay, so that's Mercian Twister versus Random Device. Now what about this uniform int distribution thing? This is really cool. It can take any of these uniform random number generators that I showed on the big slide, and which will usually output something like 0 to 2 to the 32 or 0 to 2 to the 64. However, it's not limited to that. The standard, and I love the standard, but sometimes I hate the standard. And this is one of the things I hate about it. When it says, I take any uniform number random generator, it really means any. It can have any min and any max. So if your uniform random number generator that you wrote outputs random numbers from 1701 to 1729 inclusive, which is like barely, but 4 bits, and it's not even a clean power of 2, uniform int distribution is supposed to work with that, and it will in VC. Now, if you do that, you're bad. You should not write such, like, why? It should totally require a power of 2, or maybe even 2 to the 16 or 2 to the 32. But, you know, we should write strictly correct code. And then, once it's being fed with a uniform random number generator, it'll emit any desired range of integers, low to high, inclusive, with almost any type you want. There's this thing that users have been complaining about because we started strictly enforcing this with stack asserts. It only permits signed and unsigned, char, short, int, long, and long. It does not permit chars. The standard says so. So I'm going to enforce that with stack assert and I'm done. You're out of luck. So if you're a user and you're using, say, VC 2013, which enforces this, and you want something like an unsigned char 0 to 2 to the 55, just give us an unsigned short and then truncate it down, which is lossless. I think that's actually a standard defect, that it requires these types elsewhere, and it just said int type for uniform int distribution, and it didn't mean to forbid char. It was just a fallout consequence, because there's nothing technically stopping us from working with char. But I just wanted to enforce what the standard was saying. And then, assuming that the input generator produces a perfectly uniform output, then uniform int distribution will preserve perfect uniformity using magic. That magic is basically like bit twiddling, shifting, and potentially running the input generator multiple times to retrieve the necessary number of bits. And it runs actually fairly quickly. When I implemented uniform int distribution, I didn't actually take steps to try to make it super fast, although I was paying attention to how often I was rerunning the generator. And I observed it runs about the third of the raw speed of the engine. With implementer tricks, it might even be possible to go faster. I haven't checked the other implementations. So you shouldn't be too worried about running uniform int distribution. But by the way, although the standard doesn't really say this, it's deterministic. You don't need to worry about it like varying according to the phase of the moon or something, because it's just some fixed algorithm. Your implementer is not actually trying to kill you most of the time, but it's not invariant. Unlike Mercian Twister, the standard does not specify a specific algorithm. So if you run the same sequence of numbers through VC or libc++'s uniform int distribution, you will almost certainly get different output because the implementers have chosen to implement it in slightly different ways. But it still should be the same quality. So going back to things that I hate, CS+98 has a couple algorithms, both called random shuffle. The first one is actually horrible. It can call rand to shuffle the sequence. And I put that as C++ standard library. I trusted you. Why did you betray me by calling rand? And we still do that for like backwards compatibility. I'm not too eager to change that, even though rand is horrible. So don't call that one. Rand is terrible. Then there's this other one, random shuffle, that takes what it calls an RNG. And that's the C++11 signature. It looked different in 03. It's not evil. It's actually the fundamental algorithm out of Knuth. The problem is it is super inconvenient to call because that RNG that it takes, it actually needs to be invoked with an upper bound, and then it needs to return numbers 0 to n exclusive. So the range is constantly shifting if you look at how the Knuth shuffle works. It's quite obnoxious to provide that. So you generally don't want to call that. But C++11 added a cool algorithm. It's called shuffle. No random shuffle, just shuffle. It's less typing. And you give it an iterator range, and then you give it a uniform random number generator without any sort of wrapping, without any distribution. So this can be Mersing Twister 64, or random device, or one of the others if you've got something like that. And then it's going to use that to get just raw bits, and then it's going to shuffle perfectly, meaning that all the possible permutations are going to be equally likely, which is great. And unlike other STL algorithms, which can copy their functors freely, shuffle has actually been specified to invoke the uniform random number generator in place. It is forbidden from copying. So you don't need to worry about it copying your random number generator and then, oops, if the next time you shuffle, it's going to replay the exact same sequence. It's going to run your original one in place, which is cool. So finally, just some random notes about using the random header that I've seen people run into. Although running Mersing Twister is fast to get random numbers, construction and copying isn't, because it's got like 2 to 4 kilobytes of internal state. But you probably don't want to be copying your random number generators too often to begin with, because you're going to get the same sequence of bits. Instead, you just want a single one that you're going to run continuously and keep extracting new bits from. Also, and I've actually seen parallel programmers, professional parallel programmers, make this mistake. Because uniform random number generators like Mersing Twister and uniform int distribution, their function call operators are non-const. That means that you cannot simultaneously invoke them for multiple threads. Think about it for a bit. When you invoke a random numbers generator, it's going to go modify some internal state. So the next time you invoke it, it's going to return something different. You cannot have multiple threads partying on the same random number object. Like, that's bad. Don't do that. So you probably want like one per thread using like thread local in C++11, or protected with a lock or something if you really need a single one. But you just can't have multiple threads simultaneously calling a single engine. And finally, when is it safe to skip that uniform int distribution step? I thought about it pretty hard, and the only case I can think of is when you want to map Mersing Twister or 64's output or a RAM device, which is a clean power of 2, to some other power of 2. Like, for whatever reason, you only need 0 to 2 to the 14. In that case alone, feel free to just mask off the bits that you don't want, because that is definitely going to preserve uniformity. It's simple. And it's efficient, because masking is actually going to be super fast, unlike running it through uniform int distribution. But if you want anything else, even if it's like a scaled power of 2, at that point you should be saying, you know, I'm trying to re-implement uniform int distribution. Maybe I should just let the standard library implementer do that. So yes, that's all the notes I had. But before I take questions, I wanted to show that thing that I was commenting on Andre's presentation, where, yes, because it's fun. So this is completely unrelated. But remember how he was unpacking tuples? Well, let's include C++11 stuff here. Hopefully this font is big enough. Then C++14 specifies some integer sequence stuff. I implemented it here. If you have a C++14 compiler, unfortunately, this is not in 2013. I just didn't have time. But it's specified in the standard. There are these things called compile time integer sequences. And in a note, Jonathan Wakely, who specified this stuff, shows how to use it to apply a function to a tuple. It's called apply. So using those integer sequences, which I've implemented up here, this is all you need. You don't need like 4 different helpers or anything. This simply it generates the right index sequence, like int 0, 1, 2, 3, 4, 5, and then once it generates that, it can simply invoke the functor and say get 0 from the tuple, comma, get 1 from the tuple, comma, get 2. No runtime recursion. It makes the optimizer work less hard, which is pretty cool. I also found, while implementing this, a bug in the standard, because this should not say auto, it should say decal type auto. I found a bug in VC with an internal assertion, so that was fun. But basically, the technology exists in 14 to make that easier. Okay, so I got like a minute. Does anybody have questions? There was a question over here originally. Yeah?
Can random device block?
Can a random device block? Yes. It can potentially access the OS or something else for a source of entropy. For example, in VC, we call rand_s, which calls RTL_gen random from the OS. That can totally block on something. I think Linux uses like dev random, and that can block for more entropy. Check your implementations notes. And there's a question over there.
That can be decomposed into 2 cubes of integers 2 different ways.
Yes, I did know that.
Ah, you did
it's
know
convenient
that.
how I just chose 1729 at random. Yes. Any other questions? I got like 8 seconds. Yeah, there's a question there.
What's the choice of implementation for default random engine? Is that going to be documented in
Default random engine, I am not a fan. If you look at this slide, which clicky, clicky, click, here we go. Default random engine, lower right, grayed out. Why? Because you don't know what the implementation selected. Like, the default random engine should be Mercing Twister. Don't give that choice to the implementer. Just say Mercing Twister yourself. I see no reason for that type def to exist, honestly. You can call it, you can use it if you want, but then you're, you know, why are you outsourcing your selection? It's more typing, too, than MT19937. So, yeah.
STL, we have a question from the internet. We haven't asked one for several hours. In my game, this is from somebody named Vittorio Romeo. In my game engine, I use uniform int distribution to generate random numbers through a getRandomNumber min-max function.
Awesome.
However, I am forced to construct a distribution object on every call. Is there a way to avoid that?
Sure. You can essentially write a lambda or bind, but I like lambdas, to essentially bind the uniform int distribution to your random number generator and then just invoke it as an opaque object, you know, just with 0 arguments. Now, if your concern is you've got the random number generator, the engine, and the distribution, and you need to continuously vary the range, you can either construct a new distribution every time, or I believe that there's a param, there's a way to change the range once it's constructed. That may be slightly more efficient, having implemented uniform distribution. I know how it works. We have to essentially ask the random number generator what its range is, in case it's prepared to like stab us in the back, and we need to run it more often than necessary. It's not actually too expensive to do that. Most of it happens at compile time. I wouldn't worry about constructing distributions too often. Do worry about constructing engines too often.
Awesome. Thank you, STL.